Hello, we have yet another video for you on the parallel axis theorem. This time, we want to apply the parallel axis theorem on the product of inertia. And we specifically want to demonstrate that the algebraic sign of the value of the product of inertia depends on the reference coordinate system. In other words, the sign of the product of inertia depends on the location of the origin of the reference coordinate system. We have 4 examples with an identical area, but 4 different coordinate systems. We're going to start with a centroidal coordinate system, and then we will compute the product of inertia using the parallel axis theorem on 3 different coordinate systems. Let's start with the centroidal coordinate system, and for that coordinate system, things will be very simple, as you know from the text. If you have a coordinate system with at least one axis of symmetry, the product of inertia becomes 0 for that coordinate system. In our case, we have actually 2 axes of symmetry, both y-axis and z-axis. And as such, I sub yz, the product of inertia, is therefore 0. And we don't need to apply the parallel axis theorem because there's no shift of the coordinate system outside there is no shift of the coordinate system from the centroidal coordinate system. As for the second coordinate system, which I have labeled as y prime z prime, the origin of that coordinate system is at the bottom right corner of the rectangle. For this one, the math will not be quite as simple, but it will be more than manageable. I sub y prime z prime is equal to, now this term, I sub yz, that is the product of inertia for a coordinate system that runs through the centroid of the rectangle. So basically for a centroidal coordinate system. And as you know, the product of inertia with respect to such coordinate system is 0, as we have shown here. So you can just write down 0 for I sub yz, and then minus y sub cg prime, that is the distance along the y prime axis between the centroid of the body and the origin of the coordinate system. With regard to the, or along the y prime axis, that would be the distance, let me find the space, that would be this distance here between the origin of the coordinate system and the centroid along the y prime axis. Sorry, not z, this is y sub cg prime, and that is equal to a half. And you can see that since a is the length of the whole rectangle, the distance between the edge and the centroid is just a half. And z sub cg prime, that is the distance between the centroid and the origin of the reference coordinate system along the z prime axis. I will also label that distance this is, oops, a little skewed. z prime cg, and that is equal to, now pay attention, because the distance is in the negative z prime region, the value must therefore be negative. So the distance between the centroid and the origin of the y prime z prime coordinate system along the z prime axis is b half, but because that distance extends into the negative z prime region, the value of b half must be negative. And it is important to pay attention and take into account the algebraic signs for the product of inertia, unlike with the area moment of inertia, where the distance was squared. And if your distance was negative, the square turned it into a positive value. So it was not relevant for the area moments of inertia, but it is relevant for the product of inertia. So y sub cg prime is a divided by 2 times z sub cg prime, that is minus b divided by 2, and we want to assign the negative sign to b half, and a is the area of the rectangle, that's just a times b, and if we solve this equation, we're gonna get 1/4 times a squared times b squared, and that is the product of inertia of this rectangle with respect to a coordinate system that has its origin at the bottom right corner. Now let's move on to the third coordinate system, which starts at the top left corner, and I'm gonna write down the equation I sub y double prime z double prime. I've labeled the axes with a double prime so as to distinguish between the other axes. I sub yz, and again that is 0 because this value refers to the product of inertia with respect to a centroidal coordinate system, which is 0. Minus, okay, y sub cg prime, the distance between the centroid and the coordinate system origin along the z double prime axis, and that is going to be this distance along the y double prime axis. I'm just going to write down minus a divided by 2. It's minus because the distance is in the negative y double prime region. So make sure to assign the minus sign times z sub cg prime, double prime, sorry, we have to consider that we are dealing with double primes in this case. So z sub cg double prime would be positive b half because it's in the positive z double prime region, times the area a times b, and this time the value of the product of inertia will be again 1/4 times a squared times b squared. And in the last example, where the origin of the coordinate system is at the top right corner, and we are assigning a triple prime to the axes. Again, 0 for I sub yz minus y sub cg triple prime, the distance between the centroid and the origin of the coordinate system along the y triple prime axis, and that distance is a divided by 2 positive times z sub cg triple prime, and that distance is positive b half. And then times a times b. And in contrast to the other coordinate systems, with this one, the end result is a minus 1/4 times a squared times b squared. So you see, the sign of the product of inertia depends on the chosen location of the origin of the reference coordinate system. Okay, in the next video, we will show you how to calculate the product of inertia using the parallel axis theorem on composite bodies.